Hello guys. Today we will be discussing the new xLSTM architecture. It's a let me share my screen. Yes, can you see my screen? Yeah. So today we will discuss the xLSTM architecture. It is a new variant of the LSTM architecture that I think everyone in NLP and probably deep learning knows already about. Um, So LSTM, just to give a quick introduction about the LSTM architecture. LSTM architecture were introduced as an update to the RNN architecture because RNN architecture kept having the problem of vanishing and exploding gradients. And the solution to that was the introduction of a cell state, or which we can think of as memory also. So the cell state acted both as a memory for the architecture and also something like a skip connection, not exactly a skip connection, but it allowed the gradients to flow through that to flow through, to multiple, um let's say multiple time steps back. So it allowed for better results, especially on sequence to sequence problems. And there has been many papers which talk about how LSTM architecture is fundamentally stronger than the capabilities of LSTM architecture is much stronger than the transformer models. But due to their high parallelizability, transformer models are the go-to thing or the de facto models that are used today for any NLP related task. So before we begin, a few more notes on the type of memory that was there in the LSTM architecture. So in LSTM, let's say if the size of the memory vector or the context vector was, or the cell state was 100, then all those the memory in the cell state or in the LSTM was individual and scalar points. So whenever the memory was used or the cell state was used or updated, there was no interaction between the different points or the scalar values that are present in the memory. So that severely limited uh, the amount of information or the kind of relations that could be saved in the LSTM architecture. And that is something the authors are trying to address in this paper also. So there have been a lot of search on the alternatives to transformers, because transformers have n square complexity. N refers to the sequence size here, because we have to calculate the attention values, um, and that is a attention the attention matrix is calculated between each token in the sequence. So that results in the n square complexity. So even on right now, the total sequence length that is supported is still huge. Let's say you can go up to 1 million tokens, but as you keep increasing the sequence length that you feed to the transformer model, the n square complexity makes it much more uh, memory. It makes the transformer architecture needs much more memory to run. So there have been a lot of search around like what alternatives can we have to the transformer architecture. We few weeks back we looked into the Infi attention paper, and that paper was a method to try to add memory to the attention architecture. And we also, in some time back, I think in this year starting, we looked at the Mamba architecture, which is a state space model, and we will briefly cover that also. And the main point that the authors are trying to address in this paper is like, can they bring the performance of LSTMs to the current performance levels of transformer? So um, the main you can say the contribution of in this paper is the xLSTM and mLSTM cells, which the authors have introduced, and together they make the xLSTM architecture. We will cover this in detail, so it might seem like very new terms, but we will go in detail what these two things mean. So in they are the authors are giving some new upgrades to the LSTM architecture so that they can rival the performance of transformer models. So to give an introduction of the LSTM architecture, it's good to revise what exactly happens inside the cell state so that we can understand this paper better. To do that, I will go to this particular blog post. I think it's one of those blog posts, like if you're reading about NLP or about LSTMs, you might have seen this one earlier. So, so LSTM architecture is a sequence to sequence architecture. So at each input time, an input is given, input X is given, and that input is used to calculate the hidden state, which is then used to give an output of the sequence of the model. So at each time step, the model takes in a input and outputs a hidden state. If you see here, you will notice that this bar is the cell state that we were talking about earlier, and this cell state is updated at each time step based on the values that are present in the input. So there are three major operations um, inside LSTM architecture. The first one is the forget gate operation. So what happens inside forget gate is that based on the input given and the last hidden state of the model, we are trying to understand what values are no longer needed in the memory. So to do that, we take the concatenation of the hidden state uh, and the input and the cell input, and we calculate, we multiply it with a matrix, and then followed by that we pass it to a sigmoid function. So what the sigmoid function does is basically compresses whatever representation that we have till now between 0 to 1. Once that is done, um, we multiply we multiply the previous cell state with this the values of this particular gate. So what that does is, to talk in much more simpler terms, it basically makes some of the earlier parts of the cell state forget. So what will happen is the value of ft, or the forget gate, will be between 0 to 1, and it will be um, it will be 0 for some particular scalar values and 1 for other scalar values. So that would do is update the cell state and basically remove any information that the model thinks it will not be needed in the further time steps. The second major operation that happens inside an LSTM architecture is the update step, update cell state. So since we are forgetting some things from our cell state, we will have to also add some new information to this cell state based on the input that we have. So this is a two-part operation. So we have to first calculate the values of input gate, which is denoted by IIT. So input gate basically tries to learn what sort of information should the model um, uh, what sort of information that the model should add to the cell state based on the information that we have. And another to do that, we have to first calculate the ct vector. Ct vector does is trying to come up with a representation come up with a representation yeah, come up with a representation, and that is in the same dimensions of the cell state. And what happens next is that we multiply the input gate uh, into the into this context, into the ct value, and then we update it, and then we add it to the context vector. So to again summarize what is happening here, what happens is like we try to understand what values should we save into the cell state that is represented by the ct vector here. And then input gate, basically again we multiply it to the input gate, and that converts this into or squishes all the values between 0 and 1, and that result is then later added to the cell state. So yeah, so these are the operations which take care of the cell state in the LSTM architecture. The next step is getting the hidden state from this architecture. So hidden to calculate the hidden state for this time step, which is later used to get the output, or we multiply this hidden state to to a matrix which can give us some sort of an output. Like if you are using a language modeling task, it would be a multiplication of a matrix of size the of hidden dimension times the vocabulary size of that particular language modeling task. So to get the final state, we take some input values from the cell state, and then we multiply it again with the output gate. So output gate is again the model trying to learn trying to learn what are the important values that might be good for the model to have in the representation of hidden state. So these are the three major operations that happen inside an LSTM cell. The first one is forgetting information that is there in the cell state. The second step is updating the cell state with the newer value, so that model has the information about the newer input in the memory, which can be later used in later time step. And the third operation is the output gate, where based on the values in the cell state, we are trying to, or the model is trying to learn or reason what values of this cell state are useful for the model to output. So these are the major operations that happen inside the LSTM architecture. And the three major gates that we talked about, uh, the forget gate, the input gate, and the output gate, they were all sigmoids. So um, yeah, so the sigmoids have, as I said earlier, have nice property of squishing everything between 0 to 1. So again, if you see all these equations, all the updates in the cell state that is happening here in this equation, they are pointwise. That is, each scalar value is updated without any interaction or having any understanding of possible relationship between two, or the possible relationship between the other scalar values that are saved in the cell state. So the authors then discuss the limitations of LSTMs. So the first limitation that they highlight is that LSTM lacks the ability to revise storage decisions. So the thing is that LSTM architecture has difficulty in updating the
You guys know what happened? Maybe he lost his internet. Maybe that's true. Okay, he's back.
Yeah, apologies for that. I had a network issue. Where was I? Was I absent for too long?
You were gone for about 2 or 3 minutes, I'd imagine.
Okay, okay. I'll start again. It's actually raining here, so that is why there's a connection issue. Yeah. So, so I'll continue from here. So, I think everyone got, like you were able to hear the part where I was discussing about the operations inside an LSTM cell, the revision of that, right? Um, did I lose you again? No. Okay, so I'll continue from here. So the authors here mention why what are the limitations of the current LSTM architecture. So the first issue that they see is the inability of the LSTM architecture to revise storage decisions. Uh, so what they mean by this is that currently there is no notion of importance of information in the LSTM cell state updates. So let's say if you are working on a particular task and it's a memory retrieval task, then whenever you see input representations that you think you want to remember, you would that information related to that input should have preference in the cell state of in yeah it should have preference in the cell state because of that particular task that you're trying to do. So there is no notion of weighted cell state updates in the LSTM architecture as of now. And whatever operations that happens for the cell state, they every time a new input comes, it can easily remove the information, any important information. Hi guys, sorry for this. I think there's a network issue at my place because of the rains. um, I will continue. Yeah, so Let's talk about the introductions in this paper, like the new contributions authors have made. So these are the equations that we saw in the blog post also. Here, the updates to the cell state depend on the forget gate multiplied by the cell state at the last time step, plus the input gate and the cell input that we got at that time step. A very interesting thing that we have to keep in mind right now is that the hidden state that is calculated uh, is selected by a simple non-linearity, which means that here we are basically applying a tanh operations on the hidden state, and so the hidden state that the this vector is calculated by applying a non-linearity on the cell state, and it is later multiplied by the output gate to get the hidden state of the LSTM at that particular time step. So now let's talk about xLSTM. So the to empower LSTMs with the ability to revise storage decisions, the authors introduce exponential gate and the normalization and their normalization and stabilization. So let's talk about these improvements one by one. So the one new equation that you will see here is the equation number 9, which is the normalizer state. A normalizer state is forget gate times the normalizer state at the last time step plus the input gate. So earlier we were discussing about the limitation of the LSTM architecture of not having the capability to decide which information has how much weightage. So let's see how the introduction of normalizer state helps the model to do that. So these are some equations I think which will help us understand how the introduction of the normalizer state is really beneficial. So the normalizer state at time step t is the result of forget gate times the normalizer state at the last time step plus the input gate, and the final hidden state is calculated using the context the cell state divided by this normalizer state. So let's try to open this equation and see what kind of behavior that actually ends up giving. So if we try to calculate the normalizer state for the third time step, that would be forget gate at the third time step times the normalizer state at the second time step plus the input gate at the third time step. And if we expand it, we get a value like this. So normalizer state at third time step is forget gate at third time step times forget gate at second time step times the input gate at first time step. And you can see as we increase, as we go in this particular direction, as we for the input gate at second time step, it is we are multiplying only the forget gate at the third time step. And now let's try to calculate the cell state at the third time step. When we do that, we will reach this expression of basically Z1, Z2, and Z3 are the cell input at particular time step. And when we calculate the hidden state at the third time step, which will be the cell state divided by the cell state at third time step and the normalizer state at the third time step, we will get an expression like this. So if you see here, this expression is like the weighted average of the cell inputs at that particular time step. So what is happening here is that at each new time step, the updates or the hidden state, that is the output that we get from the LSTM architecture or the new proposed LSTM architecture is like the weighted average value of all the values that are saved in the cell state. So this gives the model new capabilities uh, for for a whole lot of tasks. How? So let's say uh, we have a sequence of length 10, and somewhere in the sequence there is an important information that we have to recall at the 11th time step. Now the model, instead of the values being overwritten, the cell state values being overwritten by the time we reach the 10th time step, the model can leverage the cell state at each time step and get a weighted value from them. So this behavior entirely changes the way the memory is accessed within the LSTM architecture. Now talking about the exponential gates. So till now, in all the operations, uh, sigmoid was being used uh, as the non-linearity in the gates of the LSTM architecture. Now the authors have replaced it with the exponential function. And Yeah, and since it is an exponential function, now there is the values of the input gate and the forget gate can quickly rise to very large numbers because of the exponential function here. So to avoid that, they have introduced a stabilizer gate. So a stabilizer state you can think of like restricting the values of the input gate. Yeah. So the next introduction by the authors is the idea of MLSTM. So again, the introductions, the SLSTM architecture still is dependent on on the hidden state, and hidden state is being updated iteratively, and it depends on the output of the models from the last time step. So this is still a hindrance if we want to uh, parallelize the architecture, because if at each time step the present value of the model, output of the model relies or depends on the output of the model from previous time step, so then there is no way other than to run the model architecture step by step. So the in the MLSTM architecture, they are trying to now think of the memory as a matrix, and then the idea is that the hidden state that you get from the model is like trying to get the the information um, stored in the memory based on a particular uh, key vector, or based on a particular query vector. So now the updates to the cell state look like this. And so basically the new cell state depends on the last cell state times this particular multiplication of the value and the key vectors. We'll just see now what they mean. So here you can see, yeah. So now the introduction into this, the new introductions here are the equation number 22, 23, and 24. Now they are sort of like the query key value vectors in the attention architecture. And yet what is happening is that at each time step, the hidden state that we are this particular expression that we're trying to calculate is like the multiplication of the cell state at that time multiplied by the query vector. So this is something like you're trying to remember specific parts of the input, yeah, specific parts from the memory based on this particular query vector. And here also they have the exponential gates and the stabilizer gates that were introduced here also. And yeah, so um, so now they are now trying to view the memory as a matrix, and that allows it to store information and patterns, and do reasoning over the interaction between the values that are stored within the cell state. Now talking about the complete xLSTM architecture. So an xLSTM architecture contains both the mLSTM and the sLSTM in a particular ratio. And yeah, so if you remember the Mamba meeting, the meeting where we discussed the Mamba architecture, we don't really just put the reasoning block of the Mamba just by itself. It is part of a block. So let's see how an xLSTM block looks like. So if you can see on the left is the residual SLSTM block with poster projection. We will discuss what that is. And on the right, we have the MLSTM block with the pre-up projection, which is inside, which is wrapped inside two MLPs. So so a residual block with the poster projection, which also happens in the transformer. In transformer, first you have the attention value calculation, and then after that you have the linear layer where you try to increase the dimension of the of we basically you increase the dimension and then you further reduce the dimension again. So the idea behind that is that when you have something, this poster projection, it ends up non-linearly it non-linearly summarizes the past in the original space. So basically, it is trying to do some sort of reasoning on the already established expression, or the already calculated results. And a residual block with the pre-up projection, like which was there in the state space model, basically basically helps the model to find patterns, linear patterns in the higher dimensional space. And um the authors refer to this particular theorem, which states that in a higher dimensional space, non-linearly embedded patterns are more likely to be linearly separated. And since all the operations that you see here are linear operations, you see, they don't involve a non-linearity like softmax, which we have in the attention architecture. Here also you see all the operations here are linear only. So the idea is that in higher dimensional space, the models are much more able to effectively find patterns using linear methods itself. So the idea, that is the reason they, yeah, so that is the reason of this particular type of pre-up projection, where you increase the dimensionality size and then try to find patterns in that, followed by a reduction of the dimensionality to the original size. And uh, what are the memory and the speed considerations? Uh, Contrary to transformers, the xLST networks have a linear computation and a constant memory complexity. Why is there a constant memory complexity? Because of all the operations here are in the dimensionality space. So the maximum memory that would be used is the d cross d. Unlike the transformer models where the memory required is n cross n, which is the sequence length of the model. So the model uh, it does not require separate the MLSTM architecture does not require separate parameters, but it still it is computationally expensive because of its d cross d matrix memory and the d cross d update, which is still less because the dimensionality values can go up to like 4096 or maybe up to 10,000. But I think but that would remain constant throughout the model training part. Now we will okay, any questions till now? I know it's very hard to follow right now because of the connection breaking up again and again, but if there are any questions. Okay, we will discuss the experiment section of the paper now. Um, okay, so there's a particular notation that is used in this paper. So the notation of xLSTM the ratio of a b refers to these number of mLSTM blocks and the SLSTM blocks. So if the paper mentions xLSTM 771, that means that out of 8 blocks, 7 are mLSTM based blocks and one is SLSTM based block. So now we will discuss about the performance of this architecture on problems which involve, state tracking. So basically, like um, we'll talk about some examples of that. So these are some tasks that involve tracking of state or needs to remember something about the information that the model has seen till now. Bucket sort is basically given a string of tokens of sorted alphabet, compute the sorted string. So it has to remember what all information that it sorted till now and sort that particular string. Cycle nav is basically based on is a task where you are given a certain instructions of like you go in this direction, you move left, right, or center, and then you have to predict the final position of the agent. And other other tasks include even pairs, where we have to compute where given a binary string of A and B tokens, you have to compute whether the number of AB and BA tokens is even. And majority count is trying to remember what is the token which has come the most and what is the number of times it has come. And mod arithmetic with or without brackets is trying to solve the arithmetic operations. And so all these tasks, they require remembering information about the uh, information present in the sequences and trying to solve or reason based on that, based on specific rules. So if you see here, the performance of the model is the best performing here is the SLSTM block because of its updated memory capabilities, and it is really good in most of the tasks that are present here. Another interesting thing is the Mamba architecture we can see. So Mamba architecture here does good on the even pair task and the cycle navigation, but again, the because SLS the SLSTM block is like is has much more control over its memory, and since it's sequential in nature, so it is able to solve much better or perform very good in these tasks. Now talking about the xLSTM's memory capabilities on the associative recall task. So the idea is here is that for each sequence, key value pairs are randomly chosen from a large vocabulary, which must be memorized for later retrieval. And to enhance the difficulty of the original task, they increase the number of key value pairs up to 256, and the context length is up to 248. And here the authors also mention that since transformers have a memory that is exponential in coding dimension, which means that they are able to see the entire sequence at one go, unlike the xLSTM architectures, which at a single time step can only see one single token, and the rest information has to be stored in the memory of the architecture. So the gold standard here will be the performance by the transformer models, and you can see here as you increase the model dimension of the xLSTM architecture and the other state space based model also, the improvement on the recall task increases. And uh, and now talking about uh, the original question, like can LSTM architectures or the braided LSTM architecture perform as well as the transformers when it comes to language modeling related tasks? And here, let's look at this table. So here, they're trying to compare the perplexity of the model after training on 15 billion tokens from the Slim Pajama data set. And surprisingly, the xLSTM architecture, the of one is to zero, which is basically the mLSTM block, gives the lowest perplexity uh, as compared to the transformer models of GPT-3 and the Llama models, and the also the state space model, the Mamba and the H3 model. And so it is interesting to see that the just a single MLSTM block is able to give such less perplexity on this particular data set, which shows that it understands more about the information that is there in the data set. And talk here they're discussing about they are talking about the albation studies, and they are attributing the performance increase. And what they're trying to highlight is that does adding exponential gating and the matrix memory, how much do they contribute to the overall performance increase in the model. So So here, when they are taking the vanilla LSTM block, since if you train it for very large sequences, it will end up having very bad performance, and that is why you can see here the huge perplexity. But if you add a, a skip connection like a ResNet or a ResNet backbone in the LSTM architecture, its perplexity quickly drops because now the gradients can flow back to a much longer sequence length. And yeah, so when you add the exponential gating, which is present in the SLSTM block, this perplexity goes down. And when you add the matrix memory also, then that is when you get the least perplexity on this particular data set. So again, authors are trying to highlight that both the introductions in SLSTM and MLSTM architecture, they make significant contributions or performance enhancement to the model. Another interesting thing about this is that we know that typically in transformer models, the performance of the model starts to degrade on sequence lengths which are higher than what the model has been trained on. But we don't see that kind of behavior with the xLSTM architecture. And the xLSTM architecture performs well up to sequence length of 16,000, even though when it was just trained on a sequence length of 2048. So which which is a good feature to have. And I will quickly wrap this up now. So finally, the authors discuss about the limitations of their proposed architecture. Um, um, so the first thing is that the XLSTM architecture still relies on the inputs or the cell outputs in the last time step, which prohibits the parallelization for SLSTM. But the MLSTM architecture still allows for the parallelizability. Uh, the matrix memory of MLSTM is still D cross D, so it is not a um, it is not a still free operation as such. And here the interesting thing is that the initialization of the forget gates must be chosen carefully. And since the matrix memory is independent of the sequence length, increasing the sequence length might overload the memory for longer context size, but still this does not appear to happen for up to a context length of 16K. So that's it from my side. Any questions?